Okay, so good morning, good afternoon, and or good evening, depending where you are, and welcome to the short presentation of my job market paper, Optimal Forecasting on the Parameter Instability. My name is Yu Bai, and I'm currently a research fellow at Monash University. I obtained my PhD from local university nearly 1.5 years ago. So the full version of the paper is available at my website, and if you're more interested, just go to have a check. So the motivation of this paper is very simple. So suppose that you want to do prediction and you want to use standard linear predictive regression model to forecast the targets. And we know that under mean squared error loss, an optimal forecast will be just the conditional mean, but you need an estimate of the parameters. And equation 2, suppose that you are just using the recent unknown observations. And this is what we well known as the rolling window forecasting, right? And which is actually very popular in applied work, macro and finance. But we know that actually the rolling window for estimator here, I can write in a more general form as in equation 3. So I would have a weighting function. The shape of the weighting function is determined by a turning parameter satisfying certain condition. And we know that if the weighting function is the indicator function, if you just have this flat weighting scheme, and this is exactly the rolling window for estimator. And the window size is given by the integer part of t times b. Okay, so in this paper, we ask 3 questions. So since we're going to use the estimator to do forecasts, I want to ask under what condition on the time variation of the model parameters, and we could get consistency at the end of sample point. The second question is that you have a weighting function and you are going to use the training parameter b to determine the shape of the weighting function, and we ask how to select this parameter optimally. And we know there's perhaps a lot of research on the rolling window selection, but we want to discuss more on the general case. The third question asks that since we know that many people use rolling window, and since rolling window estimator is a general estimator of this local estimator or more non-parametric low constant estimator as given in equation 3, and we want to know that is this flat weighting function always the best choice or not? Okay, so let us start by the estimation on what condition of the time variation that you get consistency. So this is basically our environment. So we have a target and we have a predictor S, which is denoted by X, and the forecasts are produced in a rule, which is called y hat, given the parameter, and you have a loss function for forecast evaluation. And consider the general form of the parameter estimates is the minimizing the in-sample loss average and localized average by the weighting by the weight k. Okay. And on consistency, so we provide more the rigorous theoretical discussion in the appendix, and we follow closely, which is called the locally stationary framework, as in Kamakato 2022 and Dakhalos 2019, and general treatment of the locally stationary process on the nonlinear general form of time series model. because we have time varying parameters, right? If assume stationary might not be a good idea. And it's well discussed in the theory literature. And since we're using rolling window or general local estimator, the underlying assumption of the time variation model parameters will be non-parametric. So assume that the time varying parameters are modeled as a function of rescale time. And rescale that means the support is from 0 to 1. And since we care about end of sample point, which is actually theta 1, right? And we want to ask, what are the minimal conditions of this function to ensure that the parameter estimates are consistent? It turns out that it's just a condition shown here. So this is a Holder type continuity condition. It's the restriction of the amount of local time variation from the time point t to time point s. You have a normalizing kind of constant, Holder constant, or Lipschitz type constant you may wish to call, which is VCL. And you have this gamma parameter controlling for the amount of local variation, which is restricted to be there from 0 and 1. And there are examples to satisfy this condition. You could have the abrupt structural change, where you have a one-time break or multiple breaks. But as this equation shows that the size of the break must shrink to 0 as your capital T goes to infinite, right? And the second example is commonly used in the literature, which is smooth structure change. You assume more strict condition that the function is twice continuous differentiable. The cell type of this this example, the third example, the most recent literature has shown that the local estimator can also handle general type of realization of persistent and bounded stochastic process. Here I give you an example where it's scaled by the capital T, which means that it has to be bounded, and this has a D and a fractional parameter, and is inversely related to gamma to control for the degree of local variation. So let's have a look at how it looks like. So the graph here shows different the examples I have just introduced. So the black line shows that one-time abrupt changes at the middle point. And before and after that, they're all the same, but you have a one-time break. And the break size, as I have just said, the break size has to shrink as t goes to infinite, otherwise you'll satisfy the condition we just have seen. And blue line is just a smooth function, right? It's twice continuous differentiable. And red line is just a realization. Here is an example of the bounded random walk. As you can see that in this case, as the local changes are actually rough, gamma is small and the local estimator is still consistent, but it's getting harder to get precise estimates. And something more on this third case. And in general, we can write this as the equation shown here. And so you have a light-tailed, thin-tailed distribution, which is called CLTS. It must have the thin-tailed distribution, right? They kind of have a fat tail. And since it has thin tails, and I always find an upper bound of C to make sure the condition we have just seen are satisfied. So the only difference I can see that now this can see depend on T and S, but since it has thin tail, so I can have an upper bound to have the CL to bound this to make sure that the condition just introduced above is satisfied. Okay, so these are the three examples, and just to realize how it looks like. And we believe that in the first two cases, perhaps it's easier to estimate than the third case, because in third case, among the local variation are large, or somehow we're using the terminology and diffusion process, the path is rough, right? When gamma is small and probably finding some performance, so getting harder to estimate compared to the previous two cases. So it can be shown that consistent rate is given by this. So you have the first part, which is actually the usual rate variance part, and the second part is reflects the estimation bias introduced by the local estimator. It's related to gamma, and as you can see, if the gamma is small and consistent rate will get distorted, right? Okay, so this is discussion about the estimates. So since we're going to use the estimates to construct forecasts, these estimates require you to choose two things. One is the weighting function K, and the second one is the turning parameter B, right? And in the forecasting context, we care about this, what is called annual sample rest, I defined here. And it's the conditional expectation of the loss. Okay. And under certain regularity as condition, I can do a Taylor expansion around the true value θ1. And I can show that it can be decomposed into three terms, RT1, RT2, and RT3. So we want to discuss the impact on the choice of two inputs related to parameter estimates. So RT1 is not related to this, right? Because it only depends on two parameters and the function of the form of the loss function. The second one and third one are related to that. But if we're willing to assume that this conditional expectation is zero, which implies actually kind of the loss is serially uncorrelated, and the term RT2 will draw away. And what's left will be the RT3, right? So this condition I just said implies that the forecast errors are uncorrelated. So this better example, which means that this term is uncorrelated, as a score term, the conditional expectation of the score of the loss is zero, which means that this term is zero. The conditional is zero. In this case, it's just one step ahead. It means that this is a martingale difference sequence, which means that probably in a forecasting model, you have to introduce enough lags in XT to get rid of the zero correlation in your forecast error. So if I'm willing to make this assumption and minimizing the conditional expected loss, will be equivalent to minimize RT3. So we'll follow the Hirano-Wright paper, econometrical paper, to define this term as a regret loss. And I say regret, I mean, we may make wrong choice by choosing a bad K and B to when the loss to get high. So as you can see, it's a quadratic form, depends on the distribution of the parameter estimates and weighted by the Hessian, conditional Hessian, which you know at time t when you make forecasts. So how to select turning parameter? Let's just simply do by minimizing RT3 over the choice set. Remember that consistency requires that B has to go to zero as t goes to infinite. This implies that choice set, the cardinality of the choice sets, has to shrink in the asymptotic analysis. So here comes our first theorem. Under certain regular condition in the paper, we show that the optimal order of the optimal turning parameter is related to gamma in a way like this. Okay. As you can see, that is inversely related to gamma, or the effective size or effective number of observation, TB, is inversely related to gamma. When gamma is large, actually the T times B, the effective number of observations, is also larger. When the path gets rough, probably you do not want to add so many observations. You won't use so many observations to construct forecast, right? But when path is smooth and the assumption that the function twice continuous differentiable, probably you need a more effective number of observations, p times b. Okay. But the criteria is not feasible because you have this unknown parameter. This is between that, but we know that since it's consistent, that can replace by the true theta 1, right? Okay. So if we are willing to sacrifice a bit by reintroducing this assumption that the the theta is twice continuous differentiable, we can do this approximation as shown in equation 7, right? And you may say that, okay, you're introducing stronger assumption, but let's see more examples. Mostly I want to discuss more example on this third case, where the parameters assumed to be a realization of a bounded stochastic process. Consider the case that the gamma is equal to 0.5, a bounded random walk, okay? And I do this kind of simple algebra check as shown here, and we have the VT, okay? But based on what we know from the theory of the property of the bounded random walk process, we know that this term is actually bounded in probability, right? So which means that the realization of the boundary random walk process can actually be approximated by the square root function of the scale time, which means that in this case, if you consider the realization of this process, this is still differentiable. But the difference compared to the previous case is that now the bounded constant actually depends on t. This is the only difference compared to the well-known case in this type of literature where you assume that you have a twice continuous differentiable function, which means that actually it's not restricted, right? So in the Inouye et al. JOE paper, they say we don't know how to explain this, but in this case, it also works well. Of course, it works well, just using this simple algebra trick. Okay, so with this approximation, and I can do the local linear estimator to get a thetas, which actually definitely there's no gamma involved, and actually the rate would be high, the consistency rate would be better than the local constant estimator. And the difference is here, I can use this to prove the asymptotic optimality of the turning parameter selection procedure as shown in this theorem. And what does this theorem tell us? Well, it tells us that the minimization by the invisible one is asymptotic equivalent to this case where the unknown parameter theta 1 is replaced by the local linear estimate. Okay. So let us move on to the discussion of another input, which is a choice of weighting function. People always use the K1U, which is a rolling window type of estimator, which is easy to implement. But there are other choices, and recently used in applied work, for example, this K2U and K3U. K2U is an exponential type of downweighting, and K3U is a hyperbolic type of downweighting. And the differences among these three choices are actually the fact that all data are used for K2, but not for K1 and K3. As you can see in this graph, the left one is the rolling window, the middle part is the exponential type, the right-hand side is actually the hyperbolic type. Well, here in the rolling window part, the turning parameter only controls then how many observations you are going to use in estimation. There is no downweighting as shown in K2U and K3U, right? But in K3U, actually also have done this kind of truncation where the observations far away from the time you make forecast, we're not going to use that. but we are also going to downweight the recent observations. In K2U, and actually all the observations are going to be used and properly downweighted in exponential decay. The weights will have this exponential decay. Okay. Sorry. Okay. So recent empirical findings have shown that, for example, in this paper by Kapitanis et al. And Dendramis et al., and they find that they claim that using the exponential type downweighting is the best. And the finance paper in Pharma et al. In 2023 Journal of Finance, they find that using hyperbolic type of weighting function is the best. So the question is there any criterion we can provide and to guide us on the choice of the weighting function? And back to something actually shown in the appendix, and we know that the regret risk that we are going to use, right? We are going to rely on analysis of the distribution of the regret risk. Remember, it depends on theta hat times theta 1. So it's related to the distribution of your local estimator. So as shown in the appendix, and we see that actually the estimator can be decomposed into two parts. One reflects the variance, and the other one reflects bias. So in the end, the distribution of the regret risk depends on these two, which one dominates the other. And this comes to our next theorem, and depends on the condition of this turning parameter. And if this condition holds, actually it means that the estimation variance dominates the estimation bias. And the regret risk, properly scaled version of regret risk, will converge to this in distribution, something centered at 0. And in the second case, where this condition goes to infinite, and the properly scaled version of the regret risk will converge to something, probability of something, which is not 0. Means that you'll never get the mean 0 risk. And the third case would be, say, these two has the same order, and both the variance term and the bias term are all there, and you would have something like this. And what does this theorem tell us, or what we have learned? So the condition here actually all related to the gamma, which is related to the properties of the time-varying parameters, right? So which means that actually the weighting function, which actually shall be determined by the shape of the time-varying parameters, but unfortunately, these are something we never know. Okay, but in these three cases I have just shown, and actually in this case, actually the only thing related to weighting is this integral, right? And I want to, let's say, choose this scale to be smaller to get it more closer, more likely to have a 0 mean risk, which means that I want to find something like to make sure that this integral, the number is the smallest, right? In the second case, with the bias dominance, with mu gamma k, and this integral would play a role. But unfortunately here it depends on the gamma, but you can calculate what are these values when you know the gammas, okay? And third case is almost the same. And we're going to assume in the empirical application at Monte Carlo, we all assume that gamma is equal to 1. What does it mean? It means that we may fall into this worst, the bad case in which that the risk or the convert something which does not have 0 mean. But we want to have the slowest rate to converge to this bad case. Okay. And in the paper, we also have done some Monte Carlo study based on a simple DGP. It has the linear prediction regression model, which are also used in Petron, Timmerman, and Illinois. And all these type of time variation included in the Monte Carlo are considered is generally fall into these three categories of the time variation. And find out, of course, that the method is useful. It's also robust under various types of structural change. Of course, it depends on the gamma and estimation precise inverse related gamma, as I have just said. And also the forecasting performance also related to that. What about the weighting functions? Here we catch somehow the most. It's always that good to use rolling window. And this case, we do find that it does matter. But in general, that K2U exponential time weighting scheme. And so use all data and downweighting them is preferred. So in the paper, actually, we have 4 applications, one in inflation and quantile forecast inflation growth distribution on the systematic risk measure. And the third application focus on the housing, international market, and probably these days people care. And due to time constraint, now I'm just going to say something on the last application, which is the finest application on bond return predictability. So target is the bond excess return. So to find the log yield as inversely related to the log price of the N-year zero coupon bond. And this is the holding period return. So this is the 1 year holding period. And asset return is defined as return minus the 1 year risk-free rate. Okay. And we have this predictive regression. We have Pharma Bliss univariate and Cochran PLC factor and a combination of the two. It was mentioning that, okay, this is a multi-period ahead. And we may worry that, okay, the error term may not be serially correlated, as the analysis may drop the term is relevant. But as we can see that actually empirically in this example, it's okay, we still get huge gains compared to the benchmark forecast. There's some more details on how the construct of format list is just a forward rate, and Cochran PLC factor is actually the linear combination of these forward rates and how to get there. Okay, so we consider 4 bond markets. United States, the yield data are taken from Liu and Wu's paper, JP paper. And for the Canada data is taken from Bank of Canada, and the United Kingdom taken from Bank of England. And for the Japan yield data are taken from Ministry of Finance in Japan. And due to the data availability for Canada, and the sample period runs from 1986 January to sorry, this is 2022 December. So maturity up to 5 years. Sorry, this is 2022. Okay. And actually, this is the initial sample period, and so we forecast relation start at 2000 January. And maturity up to 5 years, so 16 months. And for the excess return for prediction, we consider 2 years, 3 years, 4 years, and 5 years. So forecast evaluation. Probably I should remove these clear drawings. Sorry about that. And the benchmark forecasts are standard, taking the 3 PCs from the global yield curve. If you combine all the yield curve from these 4 markets together, and the first 3 principal components, which is level factor, slope factor, and curvature factor. And the forecast relation start from the 2000 and January. This is the MC loss evaluation, right? The criteria is very simple. It's like the great loss can become this, that to say maybe worried that the error term is not serially uncorrelated, But let's see how it performs. And as I said, that the gamma shall be assumed to be equal to 1. So to implement the turning parameter selection procedure, we're going to set b equal to c times t with order with -1 divided by 3. And c ranges from 1 to 7 with a cost rate of 0.1. And c will be selected by the value minimizing its regret risk. And for the turning parameter used for construct the approximated local linear estimator, is just follow this rule sum choice by setting like this. I consider three different weighting functions as discussed before to see whether the performance matter or not. It's a rolling window, exponential type, and a hyperbolic type. And let's see the results. As you can see here, the table one shows that there's different blocks and shows you for the results. These are the results for US, and the different blocks is the results from the different different 2 years returns, 3 years, 4 years, and 5 years. And the PC yields are the levels of the MSE from the benchmark forecast. All the other entries are related, RMSE ratios related to this benchmark forecast. And in each column, I have the non-local estimator, which means that this is as forecast constructed from a full sample OS. And fixed rolling window, 60, the magic number often used in finance applications. And we have 3 different choices, all implemented with this optimal turning parameter selection by minimizing the regret loss. And the shaded entries, so the light green color, would imply that based on, say, farm up list, the specification, different choices, and this is the best. And shaded one in gray tells you, okay, so this one is overall best forecasting performance. As you can see, that gains are quite large and significant. The curves implies that it's statistically different from the benchmark forecast. It's always use this E, which indicates that it's K3U, and it's a hyperbolic weighting function. You have both downweighting the recent observation, also discuss observations far away. And as you can see that actually, if you use these predictors, actually using non-local is a full sample OS, and you cannot beat the yield curve forecast, right? Some cases okay from observation, but overall the results are not good in United States. But always best using the K3U with optimal turning parameter selection. For Canada, actually the pattern is the same, and the downside of the full sample OS more prevailed, and actually none of these cases actually can beat the yield curve forecast benchmark. What about UK? Same. And non-local estimator is still not that preferred. And these are results Japan, slightly different, but the differences are small. The gains are actually quite huge. Compared to the benchmark yield curve forecast. And sometimes you see that using the exponential time weighting is although the best, but the differences are generally very small. And we're going to move back to the K3U, it's the best if this long, and it's larger. So I just commented on the results. I just said the results are very promising, sizable, and sometimes significant improvements compared to the benchmark forecast from 3 PCs of the yield curve, particularly when K3U. So probably you need to both discard the observation far away and also downweighting the recent observations in this boundary turn example. For Japan, they're using all that is better, but differences are small. And as I said, that in many cases, it's shown that using full sample non-local estimator is outperformed by the benchmark. clearly shows that you have to take parameter instability more seriously. Okay, to conclude, so what have you learned from the answers of the three questions I raised in the beginning of this presentation? What type of time variation allowable for using, when I say allowable, I mean consistency, as well as this is called a Holder type continuity condition, which covers most of the cases considered so far and not that restrictive. And how to select the turning parameter. And just by minimizing rate risk under certain regulatory condition, and we prove the asymptotic optimality of this turning parameter selection procedure. And the third question is the flat kernel or flat weighting function always the best choice? Sorry, I made another typo again. No, but depends on the property of the time varying parameters. But in general, for all the other applications, you will see in the paper and basically find that in general, this may not all be. You could always find other weighting function which performs better than the rolling window forecast, in which you use the flat weighting function when constructing the local estimate. Okay, that comes to the end of the presentation, and thank you for listening. And if you are more interested, I encourage you to check my website. On the full paper, you will find more details here. Thank you.